the discussion of the physiological regulation of temperature in hot and cold environments. And we will study the consequences of heat stress to the cardiovascular system. So this is just as a refresher of our previous discussions on heat exchange mechanisms during exercise, where we saw that the evaporation of sweat is the main way by which we maintain core temperature within a physiological range during exercise. And this is really important because during exercise, muscle contraction increases metabolic heat production, and that will result in an elevation in body core temperature. Besides, if the individual is exercising in the heat, of course, there will be an extra source of heat that will accumulate in the body, and therefore, it's really important to rely on these pathways of thermoregulation in order to make sure that the body maintains a physiological temperature. So heat storage in the body during exercise, we know that heat produced that's not lost is indeed stored in body tissues. And this will result in an elevation in body temperature. So the body heat gain during exercise is a product of the heat produced minus heat loss. And the amount of heat required to raise body temperature is or can be calculated taking into consideration the specific heat of a human body, which is approximately 0.83 kilocalories per kilogram. Therefore, the amount of heat required to raise body temperature by 1 degree Celsius can be calculated by multiplying the specific heat of the body by the body mass in kilograms. So in the human body, we consider the hypothalamus as the body's thermostat. And actually the anterior hypothalamus is the area that is responsible to increases in core temperature. And it's also the hypothalamus, the anterior hypothalamus, controls the beginning of sweating response, so that evaporative heat loss can occur, and also responsible for increasing skin blood flow to make sure that heat is transferred from the core to the surface. On the other hand, the posterior hypothalamus responds to decreased core temperature. In other words, it responds to regulation of temperature during exposure to cold environments. And it triggers the shivering response, as we discussed before, and also increases the release of catecholamines that will result in non-shivering thermogenesis. Another response that is controlled by the posterior hypothalamus is the decrease of skin blood flow to prevent heat loss from happening, and therefore help maintaining a core temperature within physiological limits. So in this slide, we have all the physiological responses to a heat load. So technically what happens here is that the human body is exposed to a heat load, and then the thermoreceptors located in the core and in the skin, they sense the increase in environmental temperature and in body temperature, and they integrate this response in the hypothalamus that sends effector signals to induce cutaneous vasodilation and to trigger the sweating response. On the other hand, the physiological response to cold stress, we have cold, we have the receptors in the skin and in the core. The hypothalamus senses it and integrates the response and sends the effectors like shivering, cutaneous vasoconstriction, catecholamine release for the trigger of non-shivering thermogenesis, and also the release of the hormone thyroxine that will result in elevations in heat production. So in this graph, we have on the y-axis the amount of energy produced in kilocalories per hour, and on the x-axis, we have the room temperature in degrees Celsius. As we can see here, the energy output and the heat production, they are constant throughout the changes in room temperature. So in this example, the subject is exercising in a fixed intensity, at a fixed heat production, and at a fixed energy output. What is changing here is the room temperature as we move to the right-hand side of this graph. As you can see here, at rest or at the beginning of the effort, we see a greater reliance on convective heat loss. We've seen before that at rest, convection is an important pathway by which we regulate core temperature. And at a lower extent, we have the contribution of the evaporation of sweat contributing to the heat loss. As we increase room temperature, note that there is an increased reliance on evaporative heat loss, and we decrease our reliance on the convective heat loss. So this is again to make sure that at rest, convection is the major way by which we lose heat, but during exercise, especially when the room temperature or the environmental temperature increases, it increases also our reliance on evaporative heat loss. So what's the consequence of heat to other physiological systems? So we all know that the cardiovascular system is perhaps the mostly affected physiological system that suffers during efforts performed in the heat. As you know, the heart needs to pump blood to the active muscles during exercise and also to the skin so that thermoregulation can occur. So if we employ the Fick equation, we can calculate the cardiac output. That's the Q here in this equation. And this can be calculated based on the stroke volume times heart rate. And the VO2, the oxygen consumption, can be calculated when you multiply the cardiac output times the arteriovenous O2 difference. So what happens is that as you increase exercise intensity, you increase the demand for the available blood flow by the active muscles, so that nutrients can be delivered and oxygen can be delivered, but you also start generating more heat, and therefore you increase the need of blood flow to be shifted to the skin so that all the thermoregulatory mechanisms can take place. Therefore, there is a competition between the skeletal muscle and the skin for the available blood volume and blood flow. And of course, that competition, if it's won by the muscle, we are going to face hyperthermia because of the inability to thermoregulate. And if this competition is won by the skin, we are going to have an inability to provide nutrients and oxygen to the skeletal muscle, and performance is going to be negatively affected.